Okay, probability continues. Probably the last easy section here in probability. We're just going to add a little bit more to what we already know about probability. And we're going to be talking about more about independent events and mutually exclusive events that we talked about the last time. But let's get started. Okay, if you throw a single die, the probability of getting a 5 is 1 out of 6. Probability of getting a 4 is 1 out of 6. The probability of getting a 4 or a 5, 1 plus 1 is 2 out of 6. And we added 1/6 to get a 5 and 1/6 to get a 4. So in other words, can you always add in an or statement? A lot of the times you can. This assumes that getting a 4 and getting a 5 are mutually exclusive events. How about the probability of getting an even number or bigger than 3? Okay, this does not equal the probability of getting an even and the probability of getting bigger than 3, because getting an even is 2, 4, or 6, right? Getting a number bigger than 3 is 4, 5, and 6. That's 3 out of 6 and 3 out of 6. If you add those, that's 100%, okay? But that's not right. The probability of getting an even number or bigger than 3 would be, evens are 2, 4, and 6. Bigger than 3 is 4, 5, and 6. That's just 2, 4, 5, and 6. That's 4 out of 6, and it's not 100%, okay? You can add in an OR problem. You can add when there's no overlap. When there is no overlap, okay? Thus, to do a problem where events are not mutually exclusive, you must subtract the ones counted twice. We did some of that our last time together, okay? Like if you want to do the probability of getting an even, there's 3 evens. Getting bigger than 3, there's 3 of those. That adds up to 6 out of 6. But we counted the even ones bigger than 3, 4, and 6 twice. So you'd have to take 6 out of 6 and subtract 2 out of 6, and you're back to the 4 out of 6, okay? The textbook calls this the general addition rule. When you're doing an OR problem, you can add them up, but you must subtract any that you count twice. So be very much on the lookout for that. Standard deck of 52 cards. What's the probability of getting a queen or a spade? Queen, there are 4 queens out of 52. Spades, there are 13 spades out of 52, but you've counted the queen of spades twice here. You counted it in the queens and also in the spades. So 17, you've got to subtract 1 out of 52. So it should be 16 out of 52, which is 31%. Okay? What is the probability of getting a jack or a red king? There are 4 jacks, 4 out of 52. A red king, there's just 2 of those out of 52. Was there any overlap between getting a jack or a red king? No, you don't have anything to subtract. It's 6 out of 52, and I get 12%. What's the probability of getting a face card or a diamond? There's jack, king, queen, 3 face cards in each suit. So there's 3 times 4 or 12 total face cards, or getting a diamond. Are there not 13 diamonds? Right? But hold on. Here we were counting face cards, here we're counting diamonds. We counted the 3 diamond face cards here and also over here. You've got to subtract 3, makes a total of 22 out of 52, which is 42%. What is the probability of getting a red card or an ace? Half of the deck is red cards. That's 26 out of 52, right? An ace, there are 4 aces, 4 4 out of 52. But whoa, whoa, whoa. When we were counting the red cards, we counted the 2 red aces, and over here in the aces, we counted them again. You need to subtract 2 out of 52. So it should be 28, right? So 28 divided by 52, a little better than half, 54%. Okay? Watch out for OR problems. You can always add, but you got to be careful to subtract if you counted anything twice. Okay, what about the probability of not getting a black ace? There are 2 black aces out of 52, right? So we want to get any other card except 2 black aces. Would it not be 50 out of 52? Because you don't want the 2 black aces. So you can subtract. That's a lot easier than just counting up all the other individual cards that are not black aces. So 50 divided by 52 is 96% chance of not getting a black ace. How about not getting a face card? Probability of not getting a face card, I'd subtract again. There's 3 face cards per suit, times 4 is 12. Subtract off of 52, that's 40 out of 52, which is about 77%. Okay? How about if you throw 2 die and calculate the probability of not getting a 6? Well, you could go to all this trouble, find a probability of getting a 2, a 3, a 4, a 5, a 7, an 8, and so on and so on and so on, the whole way up to 12. It's much easier to subtract. Find a probability of getting a 6. A 6 could be 1 and 5, 5 and 1, 2 and 4, 4 and 2, 3 and 3. Probability of getting a 6 is 5. So subtract 5 off of 36. You want 31. Yeah? Okay? Which is about 86% chance of not getting a 6. Okay? $30 people in an auditorium, including Jack, all with different birthdays. If I place all of the birthdays on individual slips of paper and a hat, what's the probability of not getting Jack's birthday? Probability of getting it would be 1 out of 30, so subtract 29 out of 30 of not getting Jack's. All right, these are a little tricky. Let's take our time on these. What is the probability in a standard deck not selecting a red and a queen? So let's go inside to the inner parentheses. Getting a red card and a queen. There are 2 queens that are reds, heart, queen of hearts, queen of diamonds. So of getting a red and a queen is 2 out of 52. So of not getting it, subtract would be 50 out of 52 for all the rest, right? And 50 divided by 52, 96% for this one, okay? What is the probability, now watch your parentheses, selecting a red or a queen, inner set of parentheses, a red card or a queen. Half the deck is red. 4 queens in a standard deck, but I've counted the red queens in both groups. So I need to subtract 2, and that's going to give me 28 divided by 52, which is about 54%. But hold everything, I want the probability of not getting a red or a queen. So not getting the 54 subtract from 100 would be 46%. How about the last one? What is the probability of, now notice there's no inner parentheses, not selecting a red or a queen. Not getting a red would be getting a black. 26 out of 52. It's an OR. 26 black cards. Or getting a queen. There's a queen in each suit. Is that not 4 out of 52? But hold on. We counted the 2 black queens here and also here, so we have to subtract. 28 out of 52, I think we just did that one, is about 54% chance. Okay? All right. We talked about OR. When you're doing an OR problem, you can add them up, but you got to remember to subtract off if you had overlap. Okay? What about an AND problem? In the probability of an AND problem, you can multiply the 2, but only if they're independent. Independent events are like mutually exclusive. There's no overlap. Okay? So knowing if A occurs or not has no impact on B. When you throw a die and a coin, throwing a die has nothing to do with throwing a coin. So what's the probability of getting a head and a 2? Okay? Getting a head is 1/2. Getting a 2 when you throw 1 die is 1/6. Multiply 1/2 times the 6th is 1/12, which is about 8% chance of getting a head and a 2. Okay? Throwing just 1 die and asking for an even and greater than 3. We talked about this before. Are these independent? No, they are not. They're not mutually exclusive. There's overlap here. Even numbers and bigger than 3 overlap on 4 and 6, so you cannot get the 2 and multiply them. It's just not going to work. Okay? Now, where is this very useful? You have 30 Major League Baseball teams, 30 NBA teams, 32 NFL teams. What is the probability of someone picking the winner of the World Series, the NBA Finals, and the Super Bowl in 2025? Okay? No idea who's going to do that. Winner of the World Series, 1 chance out of 30. Times, there's no overlap. Winner of the NBA Finals, there's 1 out of 30. Winner of the Super Bowl, 1 out of 32 is 1 out of 30 times 30 times 32. 1 out of 28. That's not likely to happen. 1 divided by is about 0.00003. Okay? Not likely to happen. But that's the way you can do that. Because there's no overlap in an AND problem, you can simply multiply. How about the pick 3, Pennsylvania Lottery? Uses the digits from 0 to 9. What's the probability of picking the daily number correctly? The first ball that rolls down the chute, what's the probability you have it right? Would be 1 out of 10. There's 10 numbers from 0 through 9. Second ball that rolls down, 1 out of 10, 1 out of 10, 1 out of 1,000. Another way to look at this is a 3-digit number, 000 through 999. There's 1,000 of them. Your chance of getting it right is still 1 out of 1,000. Look at the lightning problem. Your probability of being struck by lightning is 1 out of 3,000. So what's your probability of being struck twice? You can multiply them as long as there's no overlap. But you have to be very careful in problems like this. What if you live in a storm zone, like say where there's tornadoes and very severe storms quite often, like Oklahoma, Nebraska, in those areas? This may not be an independent event. Or suppose you insist upon playing golf in a thunderstorm, okay? This may not be independent events. There may be overlap here because of the way you're engaging in riskier behavior in thunderstorms, okay? So it gets a little tricky in problems like that. All right, more problems. From a deck of 52 cards, find the probability of drawing a spade or a face card. Let's do it in 2 different ways. Getting a spade is 13 out of 52. Getting a face card, there's 3 per suit, that makes 12 total. But hold on, we counted the spade face cards here and here, so I have to subtract the 3 spade face cards and get 22 out of 52, which is about 42%. The other way you could do it is say spades, 13 out of 52. Or getting a face card, but I'm not going to count the spade face card, so there'd only be 9 here. 9 plus 13 is 22, and it's the same thing. Okay? Now, let's be very careful about these. A lot of these are OR problems, and you have to be very careful. It says first, here we have 76.2% of arrests are male, 15.3 are under 18, 10.8 were males under 18. There are some females in here, right? Okay, find the probability of being arrest being a male under 18. Males under 18, 10.8%. Male or under 18. Getting a male is 0.762. We want the probability of being a male or under 18. Getting under 18 is 0.153. But hold everything. When you did the males, it also counted the males that were under 18. So we counted them twice. We've got to subtract off the males under 18 that we counted twice. So minus 0.108. Okay? Add 0.762 plus 0.153 minus 0.108 is about 81%. Okay? What's the probability of the arrest being a female? Well, if 76.2% of the time it's a male, you could subtract this from 100 would be 23.8% are females. What about the arrest if it was a female under 18? We know that 15.3% of arrests are under 18 and 10.8 of them are males. Couldn't you subtract here and get 4.5% for females, right? Okay, more of these. Let's find a more exciting one. No, pop-ups. Come on. All right, try another one. Let's go down to this one. Okay, this is a good one. 48.4% of U.S. adults are male. 5.6% of U.S. adults like ballroom dancing. 3.9% of U.S. adults are female ballroom dancers. Okay? Find the probability of selecting a female adult. Well, if this percentage is male, couldn't I simply subtract 100 minus that and get 51.6, right? Are females? Find the probability of selecting a female and at the same time a ballroom dancer. Well, we know that. 3.9% of U.S. adults are female ballroom dancers. Okay, so that should be 3.9%. Find a probability of selecting a female or a ballroom dancer. Well, the females, we said were 51.6. There's the probability of getting a female. Or we want to get a ballroom dancer, which is 5.6, right? So here's the probability of getting a female ballroom dancer, getting a ballroom dancer. But in this group of ballroom dancers and females, you've got some females in here that are ballroom dancers. So we counted them twice. We've got to subtract off the ones that are female ballroom dancers, which is 0.039. This can be really, really tricky. Okay? Let's go down to this one. Find the probability of selecting a male. Getting a male, 48.4%. That's easy. Getting a male ballroom dancer. we know the percentage of adults, 5.6 of all adults like ballroom dancing, and 3.9% are females. So I could subtract that off, and that would be 1.7% are males. So what's the probability of selecting a male or a ballroom dancer? Here we go, just like this one. Getting a male, 0.484. Getting a ballroom dancer, 0.056. Just like it. Minus, now we've got to subtract off any males that were ballroom dancers are in this group. We already counted them. So I've got to subtract off male ballroom dancers. If you know 5.6% of all adults and 3.9 are females, remember, subtract, we got to subtract off at 0.017. Very tricky, okay? You see why this chapter is so much fun? Okay, this is just a really, really terrific problem. We can't do it for those of you that are viewing this online. But if you have a group of people, how many people need to be in a room before two of them share the birthday? Okay? The amazing thing about this is, like for instance, if you do the 1 minus part, the probability of not having two people sharing a birthday, if you're the only person in the room, it's a 100% chance that no one's going to share your birthday. Okay? Now, if there's somebody else in the room, so how many people needs to be in the room before two of them share a birthday? So there's a 100% chance you're not going to share a birthday if you're by yourself. But if there's somebody else in there, independent events, not sharing a birthday would be 364 out of 365 as long as he doesn't have yours. Okay, then if you'd have 3 people in the room, it drops down again. You keep doing that till it gets down to be over 50%, and it works out to 23 people. If you have 23 people in a room, the odds are better than 50-50 that you will share a birthday, which is really cool that it works out to be like that. You would think it would have to be much, much more. Okay, homework. Got some problems in the book. Okay, notice here, it says ignore any directions that insist you use a specific method. I don't care how you do them, okay? And then I got some extra problems here. Don't forget those. They are part of the homework assignment.